All right, let's look at an example where we'll test the training size, determine how many training samples we need for a deep learning model. And the results are kind of surprising. So for this example, I'm going to use Google Collaboratory, which is a free online runtime you can use for hosted notebooks, and also to use a GPU accelerator, which is really nice. So to get there, all you got to do is go to Google and search for Google Colab. Google Colab. And here it is, Google Collaboratory. All right. And when you open it, this happened to pop up with the file open, but this is what it normally looks like. But I'll just go over here and choose File Open. And I'm going to open a notebook. And there are many places I can get it from. I can look at some of the examples, some of the ones I've looked at recently, some examples from my Google Drive, or from GitHub. And I'm going to choose GitHub in this case because I want to go to my GitHub repo. I've already had that in my, I had copied that earlier. And I'll put a link to this, my GitHub, in the course notes so you can access it easily. So I'll search for that. And it shows me a bunch of repositories, and fortunately the first one that comes up happens to be machine learning, which is convenient. And it shows me a bunch of notebooks here that are part of that master branch. And I'm just going to select the MNIST training, not MNIST training, I'm sorry, training size notebook. So it opens up the training size notebook, and it has a notebook that looks very similar to Jupyter Notebook. I think it's specific to Google Colab, but it works very much the same way. And I'm going to do a few things here. I'm going to first clear all the output. All right, so I have a clean run. And then I'm also going to change the runtime type. All right, here I have a number of choices. I can choose the type, and I want to use Python 3, and I can choose a hardware accelerator, which is very nice. So Google has GPUs, or graphic processing units, available to train your notebooks, and it's much faster. It's at least 20 times or maybe 30 times faster than running on your local laptop. All right, and then I'm going to connect to the hosted runtime over here. And it says it's initializing and it's connected, which is great. So first I'll import my libraries. We've seen this before. And it gives me a warning. It says it was not authored by Google and it came from GitHub. And that's okay. It's my notebook. I know what it is. And I'm going to run it anyway. And I'm going to reset all the run times on the beginning. And okay, there it goes. And it says using TensorFlow, which is nice. And let me go down here, scroll down a little bit. And I'm going to change the number of epochs here. I'm going to change it to 20, just so that it does a little more training. All right, and we have our image size. Well, this is going to use the MNIST dataset as we did before, and the image size is 28 by 28. The number of classes is 10 in this case. And we're going to use 20 epochs and this dropout, which helps with regularization and improves the quality of the model. So I'll go ahead and run that, and it runs pretty quickly. And then I'm going to load the data here. And this is a convolutional neural network model, so it needs a little bit of reshaping. So I did a little bit of reshaping based on the number of channels, because convolutional neural networks are often used with images, and the number of channels often represents the color depth, whether you have 3 colors. And in this case, we have only 1. We have grayscale, so there's only the color depth is 1. All right, so now let's train this model and with different sizes of input, or different training sizes. So I'm going to train it with 100 samples, 200 samples, 500 samples, 1,000 samples, and so on, up to 10,000 samples. As you know, we have up to 60,000 training samples available in the MNIST dataset. I'm just going to go up to 10,000 in this case and just capture the accuracy for the test data each time I run it, each time I train it, and then plot out what that accuracy looks like for different sizes of training samples. So let's go ahead and run that. It gives us a few warnings, which we'll ignore for right now. And So first it says 100 samples and the accuracy is 70%, 200 samples, 79%, 500 samples, almost 90%. So it's actually quite good. And you notice it runs pretty quickly because we're using a GPU accelerator, hardware acceleration. So 2,000 samples, 5,000 samples. So we're up to 96, 97% with just 5,000 samples. So that's encouraging. So that means that even with 500 or more or under 1,000 samples, I'm already up to 90% accuracy. So if I need to label something manually or by hand, I only need, say, a 500 or 1,000 samples with 10 classes or 10 different categories. And 10 categories, statistically, would only be about 10% accurate if I was just to choose randomly among them. So you can see that the model is actually doing fairly well. And so clearly, it definitely gets better with more training data. So let's try another experiment. So that's with 10 classes, right? And 10 classes meaning there are 10 digits, 0 through 9 that we're going to choose from. So let's try something else. In many cases, we can solve a much simpler problem. And the simpler problem we're going to solve in this case is just binary classification. 2 different categories. And this is a good business case because many problems can be divided into good or bad or true or false, important, not important, fraud, not fraud, and so on. Anomaly, not anomaly, something like that. And what I'm going to do is I'm going to change the number of samples that I'm going to use here simply because we'll see. In this case, I'm going to choose binary, and we'll see that it doesn't take many samples at all. And so therefore, I'm going to reduce the number of, and I'll put one more, 2,000 here. Okay, and I'm going to choose 2 classes in this case, or 2 categories, the numbers 8 and 9. And I chose 8 and 9 because they are visibly kind of close together. If I was to choose 0 and 1, they're quite different visually. So it doesn't take much to train that at all. So I'm going to just choose 8 and 9 just to demonstrate something that's fairly close. And in the beginning of this training set, what I'm doing is I'm going to go through all the training examples and choose the ones that correspond to the numbers 8 and 9. I want to exclude all the others, 0 through 7. I just want to use 8 and 9. And I'll do the same thing for the test set. So that's all I'm doing there. And then I'm going to use this XTR, which would be my training and test and training set. I'm a training set, sorry. And then the XTE I'll call my test set. Not the best variable names, but it's okay. All right. And then the rest of the code pretty much runs the same as before. And I'm going to plot out the accuracy. Let's see how this runs. And you see right off the bat with 10 samples, we're already at 86%. Then it drops a little bit down to 77. So there's a little variation there. And then it's up to 90%, 94, 95, 97, 98. So it seems to have stabilized. And so you can see when I plot it out, early it maybe has, you might call it beginner's luck, right? It happens to do very well, then it's not so great. But even with 100 samples, it's over 94%, and it seems to be very stable after that. So it doesn't take many samples at all if you have a good model and if you choose just a few classes. Like in the case of binary classification, just a random choice would have been 50% accurate. So the model doesn't have to be that good. So you can see that if we just choose the problem correctly or restate the problem, we may not need lots of labels. And easily a few hundred labels, anyone can manually label that in a reasonable amount of time, maybe even a day or in a couple hours or something. So it's not something to start with. And later, once you have a little bit of accuracy or a little bit of improvement in your business process, you can think about adding more labels and getting better accuracy with more classes. So this shows you don't really need many labels for classification.